Hi everyone, and welcome to Zeros. Masco, yes, I know, he's looking at me to say, what are you talking about? Well, lots of people said we haven't seen Zero for a while, and that's probably because I haven't done any Zero puns. But for those of you out there, hi guys, here's Zero again, he's still good, and thankfully you don't have smell-o-vision, because if you had smell-o-vision, wow, he's a hot dog. Today's been a hot day in Australia, and as such, he a little bit stinky, aren't you? But, say bye-bye, because we're going to do a mass video. Bye-bye. Whee. All right, well, there's that, and that's Zero, and he's now going to lie down for me. But we're dealing today with the graphs of logarithms, which is a continuation of this little short section of videos I've been doing on logs and exponential functions. And you probably just saw a shadow behind me as the dog cuts my lights. That's fine. Now, by the end of this lesson or video, I'd hopefully very much have you learn what the graph of a logarithm looks like. Now, actually, funnily enough, in the previous video, if you haven't seen it, it's just great. We did something on logarithms and how it compares to exponential graphs and what we can glean from an exponential graph to help us with a logarithm graph. Now, way back when the dinosaurs roamed the earth, and this was a video about 3 videos ago, we looked at a graph of exponentials. And the example we used was the graph y equals 2 to the power of x. Now, we've been dealing with this, solving logarithms and all sorts of stuff, and we were told that the graph of y equals log base 2 to the x was the inverse of y equals 2 to the x. Now, how did we do that? Well, firstly, I sketched the graph. And so this one here is basically y equals 2 to the power of x, and this one here is y equals log base 2 to the x. Now, sketching those two together, it became pretty clear that they were the inverse of each other. How? Well, firstly, that one crosses through 1 on the y-axis. This one crosses through 1 on the x-axis. If we look to this point here, it was the point 1, 2. If we look to this point here, it was the point 2, 1. And actually, for all points along my graph, if I looked at this point here, which is obviously 4, 2, I'm pretty sure there would be a point on the graph y equals 2 to the power of x of 2, 4. In fact, we already know that. Now, knowing that really helps us sketch the graphs of logarithms, or it can help us sketch the graph of logarithms. What is very important to know, as I say here, is that where our asymptotes are, whenever you sketch graphs, you must put where your asymptotes are. Without it, unfortunately, you lose a shed loads of marks, and I did say shed loads of marks. All right, so the last thing I'm saying here is please remember that exponential functions are one-to-one functions. Again, that comes in handy a little bit later on. You know, people walk up to me and go, do you know what, Darren, what happens when you change the base of a logarithm? And I go, who are you? No, I don't. No one's ever walked up to me and said, what happens when you change the base of a logarithm? I'm always happy for the first person to do so. And maybe one of my 7 subscribers will do that for me. Hey to you today. I hope you're well. But anyway, well, what actually happens is this. So looking at what's behind me, we can see that there are 3 graphs here, and they may well be log base 10 of x, log base 5 of x, and log base 2 of x. There may also be something completely different. Who knows? I didn't label them. That was a bit remiss. Anyway, but what we notice is 10, 5, 2. If I had a 3, a 7, 1,000, a million, all of the graphs would actually have the same shape, and that is this shape here, where they all go through 0, 1, and all have that sort of curve. There is an asymptote down the line x equals 0. And generally speaking, they'll all go through various values. Now, as I said, that is for values where if you have log of x to the m, when this value here is greater than 1, they all have this, shape. But what actually happens when the values of that base fall between 0 and 1. Now, first things first, you can't have a negative base. Doesn't make any sense. But if I was to do, for example, log of 0.1 to the x, the log of 0.5 to the x, or the log of 0.2 to the x, well, they all still cross through 1, 0. But now, rather than doing this, they do this. Whoa, and actually that looked exactly the same, didn't it? But that against that. So it's important when you graph these things that you make sure you note what this value is here and how the graph's going to look. Yes, it still has an asymptote at x equals 0, but in this situation, rather than going from the y-axis close to the y-axis and up, it's actually coming close from the y-axis and down, still through 1, 0. A minor point and not necessarily massively important for what I'm going to do for the rest of this video. Now, Those of you here in Australia will spend an inordinate amount of time in year 12 actually doing graphs of translations, dilations, and reflections. In fact, about, I think, 2/3 of the course deals very much with graphs. It is full on. And if you can get methods 1 and 2 and any pre-learning done now and remembered, then I think the rest of the course becomes relatively simple. One of the things we get very, very ecstatic about in methods is the idea of inverses. And not just inverses, domains and range of functions and their inverses, and blah, 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 blah. Now, we've already met in previous videos how to find the inverse of something algebraically, but those have been inverses of basic functions. Now we're going to start looking at exponential functions. So an example of an inverse of the function given by that, if you remember, an inverse is where a graph is reflected in the line y equals x. So a graph is reflected in the line y equals x, which actually is the hint in how to do this algebraically, because every x value becomes y and every y value becomes x. And so taking my function of y equals 10 to the power of 3x, my inverse can be written as 10 to the power of 3y. Now, that's no use to me because we always write our functions in terms of y equals. So in this situation, I now need to do something to get that y down. Well, it's in a power. So, using information from my previous video, what can we do? Yes, we can take logs of both sides. So I'm going to take the log base 10 of x is equal to the log base 10 of 10 to the 3y. Now, if you don't know why I've taken log base 10, it's because of this 10 here. Because when I take log base 10 of 10 to some power, then they effectively cancel out, which gives me that 3y is equal to the log base 10 of x. And dividing both sides by 3 gives me that y is equal to 1/3 log 10x. Now, I know some of my students actually get a little bit perplexed by this whole third thing. If I go back and say 3y is equal to log base 10 of x, many people want to do this. They go, log 10 of x all over 3. And I go to them, well, yes, but that's exactly the same as 1 times the log base 10 of x on 3. And they go, yeah, that's fine. And I go, well, there is your third. I can actually write that as 1/3 times the log 10 of x. Now, if you're not sure how to do that, I can't tell you enough. Please practice. It is so, so critically important. But finding the inverse of a function, swap the x and the y, and then manipulate it to get y equals. What about this one? Find the inverse of the function defined by g of x equals 4 log 10 3 of x. Now, there's two tricks here. Firstly, they're giving me a log graph. Secondly, they've given me this number in front of my log. So the first thing I'm going to do is I'm actually going to say, well, I'm going to write this out as y equals 4 log 10 of 3x. I don't have to be g of x, doesn't help me. And I'm now going to swap my x and y because the inverse has the x and the y swapped. So x is equal to 4 times the log base 10 of 3y. I'm looking to get my y on its own. So first thing I'm going to do is get rid of that 4. So I get x divided by 4 is equal to the log base 10 of 3y. And lots of people go, well, what do I do now? Well, remember, if I do log base 10 of 10 to the x, remember they cancelled each other out, leaving me the x? Well, what I do forwards, I can actually do backwards. So if I was to do 10 to the power of log base 10, 3y, well, if log base 10 of 10 cancelled out, also does the power of 10 to the log of 10. They also cancel out. So what I need to do is raise everything to the power of 10. So 10 to the power of x on 4 is equal to 10 to the power of log 10 3y. They cancel each other out. So I get 3y is equal to 10 to the power of x on 4. Taking out 3, I get y is equal to 1/3 times 10. Let's actually make that look like a 10, not a log. 10 to the x divided by 4. So that's sort of an overview of how to do inverses algebraically. One of the things the methods course gets very, very excited about is finding domains and ranges of functions and their inverses. And I have said in many videos before, and I will say over and over again, the best way to find an inverse, the domain and range of an inverse is to find the domain and range of the original function. Now you're going to say, if I look at this function I've given you here, it's actually x squared plus 2. Now you're going to turn around and say, well, hold on, that's a parabola. And I'll say, yes, under normal circumstances, but you'll also notice that I've limited my domain because I can only find an inverse for a function if it's one-to-one. And remember, to have a one-to-one function, it has to be able to pass the horizontal line rule, as in it'll only cross that graph once. So having got all of this right, there is my function. If I look at my domain and range for that function, my domain for x squared plus 2 is, well, basically 0, because it includes 0. I'm actually allowed 0, so I'm going to put that in the square bracket, to infinity. And what is my range? My range is all possible y values, which again is 2 to infinity. So that's the domain and range of, let's say, my original function. Now, this red line is my inverse. If I was to algebraically say y is equal to x squared plus 2, so x becomes equal to y squared plus 2, so x minus 2 is equal to y squared, and so y is equal to plus or minus the square root of x minus 2. Now, basically, there's your x minus 2. Now, you'll say, but the plus and minus is missing. Yes, it is missing, and that's very much because the plus means that it's the section of the graph above the x-axis, and the minus actually would give you a section of the graph below. So we now know that this function here and this function here are the inverse of each other. So let's now look at the domain and range for the red line. So the domain of my red line is equal to 2 to infinity, and my range is equal to, well, in that case, 0 to infinity. And what do you notice? And this is the big takeaway for these. Did someone say takeaway? I'm hungry. The big takeaway is that whatever the domain and range is for my original function, you just switch them for my inverse. Because I'm swapping my x and my y values around for my function, then my domain and range must also switch. And there's my domain was 0 to infinity, my range is 0 to infinity, my range was 2 to infinity, my domain is 2 to infinity. So drawing these things is actually really useful to us, because if I know the domain and range of the original function, I can find the domain and range of my final function. So, ladies and gentlemen, find the rule for the inverse function of log 2 x minus 2 and state the domain of f to the minus 1. Now, what I'm actually going to do is very quickly, I'm going to draw that graph. That's my original function. So, the log base 2. What does a log base 2 graph look like? It looks like that. I know that's going to cross through 1. And I know over here it's going to cross through 2, 1. Why is it going to be 2, 1? Because of that little 2 there. Now, that's the base graph, but this x minus 2 is a translation. So it moves it 2 units to the right, which I think is that way on this. So move the whole graph 2 to the right. That means my x values change by 2, which gives me, it was 1, so it's going to become 3. And my x value there was 2, so it's going to become 4, 1. Now, that's sadly not the end, because I had a asymptote, which I now need to make sure that I move as well. So my asymptote now becomes x equals 2. So how does that help me with my domain and range? Well, now, for my original function, I know that my domain, all possible x values, are given by 2 to infinity. Why 2? Because that's where my asymptote goes, right? So my asymptote moves over. And my range is actually all real values. Yes, my graph will literally go from minus infinity to plus infinity. There's nothing stopping it. Knowing that information, and you're thinking, wow, this is a lot of work for one question. It isn't, because you get quicker at this stuff, I promise you. But what now happens is, I can find the inverse of this function algebraically. We've got y is equal to the log base 2 of x minus 2. First thing you do when you find an inverse, swap the x and y. So there's my x is log base 2 of y minus 2. Now I'm going to get a y on its own, which means I need to get rid of this log base 2. Well, if it's a log, I need to raise everything to the power of 2 to get rid of that. So 2 to the power of x is given by 2 to the power of log 2 of y minus 2. Well, they cancel each other out. So 2 to the power of x is y minus 2, or y is 2 to the power of x plus 2. So there we go. There is my inverse function. There is f to the minus 1 of x is equal to 2x plus 2. How do I now find my domain and range? Well, I don't want to draw that. Well, I don't need to, because using the information here, I now know my domain is real and my range is equal to 2 to infinity. Job done. Right? Really like the idea of drawing these graphs. Now again, if you're a lad or one of the lads or I don't know, a stereotypical boy, of which apparently I am as well, then you won't want to do any of that. You'll just try and visualize it and get it right first time. Yeah, it doesn't always work out for you guys, sadly. Now, last section for this graph video before I move on is about transforming graphs. Just when you thought it was safe to get into the water. And I'm sure there is a shark crossing here somewhere. Just love this. Transformations are literally in everything. I keep saying this in all of my videos. I want to sketch the graph of, that is actually supposed to be a, let's make it a 10. All right, it shouldn't be an x, it should be a 10. That makes no sense. Sketch that graph and state the maximal domain, the equation of any asymptotes, and the x-axis intercepts. So, first things first, I'm going to draw a quick sketch of my graph of log to the base 10 of x. A quick sketch like that. That goes to the point 1, and I know that there will be a point over here of 10, 1. Again, why is it the 10? Because of this value here. I'm moving it minus 2 again, so that now becomes 3. That becomes 13. And I now know that I've got an asymptote which will cut down here at the line x equals, no, not 3, x equals 2. So, that is my graph of the log base 10 of x minus 2. Again, all I've done is use the previous learning to help me build up this graph. State the maximal domain. The maximal domain and domain are pretty much the same. To be perfectly honest with you, there's a subtle distinction. So, I'm going to write the domain. Now, you should really start writing domain as x and that little e. So, my domain, my x values, are a set of... what do we say there? 2 to infinity. Now again, remember it can't include the value of 2 because this graph gets closer and closer and closer to the asymptote, but it never ever touches it. So there is my domain. The equation any asymptote, I've already put it on the graph, so thank you very much. I'm going to label that y and I'm going to label that x. And it wants to know any x-axis intercepts. So it wants to know this point here. Now, it's not 3, or is it 3? Oh, hold on a moment. Yeah, actually, my x-axis intercept is actually 3, 0. Now, if I wanted to prove that algebraically, how would I do it? Well, I know that the x-axis intercepts are given by the point y equals 0. So, if I was to have 0 equals log base 10 of x minus 2, right, same rules apply. I want to get rid of this log 10, so I need to raise everything to the power of 10. So, 10 to the power of 0 is equal to 10 to the power of log 10 of x minus 2. They effectively cancel each other out. Now, 10 to the power of 0 is 1, because anything to the power of 0 is 1. That becomes x minus 2, and we have a beautiful little equation that gives me my x value is equal to 3. Now, there are probably thousands of examples I could do in these, and I wish I had the time, but I'm trying to keep these videos short so you understand the theory, where it comes from, and a couple of examples to help you go forward. As always, it's great to see you, all 7 of you, who I believe are probably somewhere in Hull in the United Kingdom. Yay! Great! Thanks very much. Hope Hull's good. I'm missing the homeland. Otherwise, do me a favour, guys. Get out there and get people to subscribe. It would be greatly appreciated. And let's do some battle against people who seemingly, I don't know, get millions of views just for cooking an omelette. I don't get it. It's weird. If you haven't subscribed, do me a favour, subscribe there for me. Thank you so much. And if not, hey, watch another video. Try and decide whether it's worthwhile. Another video loading for you over there. Say hi to anyone you know. Spread the word. I look forward to seeing you next time. This is Masked Guru, signing out.